Let's start with a displacement time graph. Okay, let's say x there for displacement and t there for time. Now, just to have something to think about, we can let us imagine that what this is about. This is about say a child, okay, walking along a path, right? And we are going to think of this path as the x-axis, and the child, let's say the child starts at x equal to 0 and starts walking, right? So so his position, all right, at any point along the road is given by x. Okay, and when he is or she is at x, let's say the time is t. Let's say I then plot a graph of x against y, and get something like this. Get a straight line, sort of roughly straight line on the graph of x against t. Now, if I think about if I start thinking about the velocity, right, I can think about getting the velocity from this graph. Okay, let me draw the axis for velocity. So t and v. Now, to get the velocity, I can imagine, let's say at a certain time, I can imagine thinking about a short time. Now, a short time, let me call it delta t. All right, the symbol delta is often used to represent, to mean a small change or small interval. Let's say over a small interval of time. Now, I'm going to find out from the graph how much x increases during this time. So this is how I do it. I read off the corresponding interval of x from the graph, okay, and I call it delta x. So that's one way to think about it. The other way to think about it, which I've seen earlier, is that we can think about think of the gradient of this part of the graph. Let's say I draw a horizontal line here and here. That gives us a right-angled triangle, and the vertical part here is just the delta x, and the horizontal part there is just the delta t. So we can think about in terms of finding the gradient, all right, that the gradient gives the velocity. So in any case, I can, from the displacement, I can just read off, I can find out the velocity. Now, since if this is actually a straight line graph, then the gradient is going to be the same at every point along the graph, meaning that my velocity would be just constant. All right, at every second, the displacement would change by the same amount. So that just means a constant velocity. In which case, I can imagine that let's say the velocity, if I plot the velocity at the start and I get a point there, then after a short time, it's still the same velocity, and after a short time, it's still the same velocity. So I'm just going to keep getting points at the same velocity, and that would give me a horizontal line. A horizontal line. So that's what we can understand from the graph. All right, what we can learn from the graph. Now, I'm now going to look at something slightly more complicated situation. Now, suppose now that the boy starts running, and suppose that he starts slow, and then he picks up speed, and then he runs faster and faster, and he accelerates, right? And he was able to keep this up for maybe 1 or 2 minutes. So during this 1 or 2 minutes, he just keep going faster and faster. Now, if that is the case, then we would not get a graph that looks like this, right? We will not get a graph that looks like this because a straight line on the displacement time graph, as we have seen, shows that the velocity is fixed. So if we keep going faster and faster, what would the displacement time graph looks like? Let's draw another one. Another graph. X-axis, t-axis, so time and displacement. If the child is accelerating, the graph would look like this. It would curve upwards. Why would it curve upwards? Well, let's do our time interval thing again. Now, let's say I think about a short time, maybe 1 second or 0.1 second, alright, a very short time, which again I'll call delta t. So in this very short time, he runs a certain distance, okay, and that distance we can find from the graph. That's my delta x, so my small change in x. Now suppose so that I go to a later time, okay, but I think about the same time interval, the same t. So maybe this is 0.1 second. Okay, so just to make things easier to imagine, I'm going to call that 0.1 second, and then I also look at 0.1 second at a later time when he's running faster, actually. So at a later time, I can also find out during this short interval what displacement you would have. Okay, the delta x at a later time. And you can see from the graph, because this part of the graph is deeper than this part of the graph, so clearly this interval is bigger than this interval. Right? There's a bigger displacement at a later time. And that's expected because he's running faster. So in the same time he would go further. Okay. So the slope of the graph actually increases because the speed increases.